we will unmute you, or you can put your questions in the chat functions, and then we will actually work that way to answer your questions. So the webinar was started by the publication of a white paper called Thermal Runaway on Schottky diodes. That's what we're going to discuss in detail, but we're also going to talk a lot about Schottky technology and hopefully provide you a better understanding of Schottky technology, so you can improve your own design and take care of not only thermal runaway but also the other aspects of Schottky technology that you may want to use in your design. So we're going to talk about Schottky technology here. We're implying that this is the front end. So how you make the wafers, the definition of the maximum junction temperature, which is not that straightforward. Then we're going to go into detail of the thermal runaway effect on Schottky diode. We're going to talk a little bit more about reliability and the junction temperature of a Schottky. Then we're going to talk about second sourcing Schottky diodes and datasheets, a little bit more on datasheet analysis. Then we're going to go to backend technology, because there are some actually some new packages available that actually improve Schottky design or the use of Schottky in your application. And then we're going to talk in general about conservative design, or how you can get to the best you can do to go to zero defects, to get to zero defects on Schottky diodes. Let's get going by talking a little bit more about the front end of a Schottky diode and how it's manufactured. This is a simplified, on the top left, a simplified Wikipedia drawing. You'll see the top metals, the epi substrate, and then the smaller thing is the barrier material, which is also very important. The P plus should be in the yellow, and that is actually what they call the guard band. So the VF of a Schottky diode is actually determined by two things. So it's determined or by three things. It's determined by the barrier material, it's determined by the breakdown voltage, and it's determined by obviously the die size. The die size in this case is obviously a cost factor. The barrier material, we're going to talk a little bit more in detail about that in a later slide, but that always has a VF-IR leakage current trade-off. So there's no such thing as the perfect barrier material. You can reduce the VF of the barrier material, but that will automatically increase your leakage current and improve your chances of, unfortunately, of thermal runaway. The breakdown voltage actually is, we're going to look a little bit in the bottom, in the top left side, you see actually that's a planar MOSFET, but the electrical field is actually quite similar to a planar Schottky diode. So what happens if you have a reverse voltage, it will be taken care of by the P plus guard band, but there is an electrical field over the epitaxial diode that shouldn't go to punch through, and as a result that needs a certain dopant or a certain resistivity. And that resistivity, of course, it impacts the VF and is linked to the breakdown voltage. So there's not much you can do about that. If you have a 100 volt or a Schottky diode, then there has to be a certain resistivity available to handle the breakdown voltage. So, or 120 or 150. So there's little opportunity in this case to improve the VF. I think this structure is already known since the 80s at least. So it's a long established technology. Of course, there are more complex, the complexity has increased. So you can now also have better passivations available and much more mask layers on these structures. But the long established technology has little room for improvement on the VF. So what we're looking at again is this electrical field, and the analogy is there. So also in, let's say, in a planar MOSFET, you want to move away to either super junction structures, or in the case of low voltage, to split gate technology to get the field away from the surface and to actually reduce the resistivity of the epitaxial layer to get the VF or the RDS improved. That's what we're doing actually at trench Schottky structure. So we're making the field what they call non-linear. So you move it away from the surface, you move it maybe to the bottom of the poly. We'll talk a little bit later on that in detail. But so what you can do is reduce the doping of the epi in this case, and you improve VF. The higher the voltage, the bigger the improvements you can make. You can't make that much improvements in 40 or 60 volts. You can make some, but your main improvements are going to be in 120, 150, 200 volt range. And that's also why these days you have also higher voltage Schottkys that are significantly more competitive. So if you if you would define the figure of merit of a Schottky diode as the multiplication of the VF and the IR, then obviously the figure of merit of trench Schottky is better than planar. So you will have either a better VF for a certain die size, or for a certain VF a better IR. So you can reduce the die size with the trench Schottky, but you can also improve, for example, or increase the power for one package. So you can make, you get more power or more efficiency out of one package. There's a lot more design variation. You have a nonlinear field. Everybody is on recipe here. The trench depth you can vary, the distance between the trenches, and also the oxide thickness. So everybody has their own recipe here, but the field is usually the strongest at the bottom of the poly trench. So it's all great. I mean, the trench Schottky is definitely an improvement in technology, but there is also, of course, a downside. There is an increased complexity and cost. It's much more difficult to make. It also requires a significantly more advanced fab to make. And we're talking here about 6 to 8 inch fabs, whereas planar Schottky usually is on 5 inch. And also it has low revenue per wafer versus other fabless products. So that's something you see in these times with the extending lead times and that type of stuff. If there is a shortage, then of course the products with the lowest revenue per wafer will be impacted more than other products. And that, of course, is another issue you have to take care of with trench Schottky diodes. Maximum junction temperature, we'll talk a lot about that later on also, but it can actually be useful for things. It can actually determine the current rating. So the current rating, is in the derating curve, how far you can go on the maximum junction temperature. It should set reliability testing, but maybe not everybody has the same rules for that. It should be clear on ACQ 101, but maybe for non-automotive parts, there is a bit of liberty and freedom. Of course, the maximum junction temperature is determined by the thermal runaway point. The formula is written there, and actually what you do see in this case is that the thermal runaway point, or the maximum junction temperature, is oddly enough dependent on the thermal resistance. And it can be used to calculate long-term reliability via Arrhenius or Coffin-Manson. So those are 4 different uses of the maximum junction temperature in a Schottky, which people may have different interpretations for between different suppliers. So that's something to keep in mind when you look at a Schottky datasheet. Let's look a little bit more at this barrier material, which is the more black magic part of the Schottky technology. There is, of course, the link between the barrier material we use and the TJ Max. So, and the barrier material and the TJ Max are also linked to the leakage current, and that's going to be important if you have thermal runaway. So when we say something is 175 degrees C rated, it should have a higher VF than 150 C rated product for a similar die size. So the higher barrier material with a lower leakage current obviously pushes up also the VF. Now, there is no such thing as 2 different barrier materials, 150 degrees C and 175 degrees C barrier material. There are actually dozens of barrier materials, and every supplier has their own recipe, and they're all secrets and that type of stuff. These barrier materials are in general alloys. They're platinum based, and they have various amount of silicite in them. There are also other older barrier materials still around, but that's how most of the new ones are made. So all these different barrier materials and combinations are then grouped into categories by marketing people. And we're either going to call them 150 or 175 degrees C barrier material. Or the second thing that could happen is then, you call them ultra low IR or low IR or something like that, other marketing names for these type of barrier materials. So there is a link to reliability testing, but not every supplier here has the different or has the same definition or understanding of what a barrier material is, or if it's 150 or 175, or they're all different. There are dozens of different barrier materials around. So the leakage current is also obviously dependent on the die size. That's another thing we should mention on this slide. So this is something you should understand here about barrier materials and how this will impact your design. So we actually decided to revisit thermal runaway because thermal runaway actually happens if you have a high ambient temperature, high power dissipation, and high breakdown voltage, the combination of high leakage current losses. That happens a lot in LED lighting. That also because you have longer strings than LED if you design it with long strings, with lots of them in series. Automotive designs is not just polarity protection anymore, but you see also on the 48-volt boards that there is also switching application, so that actually gives you the potential for thermal runaway. Of course, trend Schottky pushes the Schottky diodes up to 150 and 200 volts, so that is another reason why you can have a lot of leakage current losses. And in the old days, a TO220 on heatsink was a very well established and recognized design. But if you go into surface mount power, maybe you are less knowledgeable about your junction temperature, and you can also get into troubles in those areas. So there's lots of people pushing their Schottky these days with a higher ambient temperature and also with a higher breakdown voltage. So that actually is an area where you see thermal runaway happening. The next slide, or before that, we're going to the thermal runaway explanation. We're going to look a little bit into detail into Schottky data sheets. So I took here a new diode which we made in this exposed package, this SMPC 4.0, sometimes also known as a TO277, and we made a new diodes with 100, 120, and 150 volt breakdown voltage. We're going to look into detail on the 150 volt breakdown voltage part. But as you can see here, actually, the VF of these products is actually fairly good. The 100 volt part has 0.66 volts. So that's 660 millivolts at room temperature, 5 amp is a fairly good spec. There is, of course, a trade-off that in this case, we made the leakage current a little bit higher with the barrier material. So these are the diode we're going to look at a little bit more in detail. So it's trend Schottky optimized for VF, has good VF. It has maximum IR data actually here on leakage current data at 125 degrees C. And the exposed paths can actually help the Schottky diodes because if you dissipate a lot of heat, then exposed paths can be beneficial. Let's look at leakage currents first. This diode is characterized up to 150 degrees C. So the main problem with thermal runaway caused by thermal runaway is, of course, that the leakage current has a positive temperature coefficient. That may not bother you too much in a 40 volt Schottky diode, but as you can see here, 80%, we're looking at the 150 volt diode, so 80% is 120 volts or something like that. Once you go to, let's say, 125 degrees C, 1 milliamp, you're talking about 120 milliwatt reverse power, which can actually go up here. And then those reverse losses actually become significant. Important to notice here, this is an old rule people used to say actually in the 80s and the 90s, sometimes this is lost. In modern days is use your Schottky diode at 80% of the rated voltage. You can see the reason here is that of course, these are logarithmic curves for the leakage current, so you have to watch out a little bit. But you can see the leakage current going up linearly until 80% of the breakdown voltage, and then you can see it go up a little bit more, and you're going to get round characteristics, especially at high temperatures and that type of stuff. So leakage current have a positive feedback or a positive temperature coefficient, so they are the cause for the potential instability in a Schottky diode. Forward characteristics, so normally the dominating loss in a diode is, or in a Schottky diode, forward characteristics. It's easy to see. I mean, you have 5 amp here, and you're going to go, let's say, at 500 millivolts or something like that, or in this case, 600 millivolts. Then you're talking about 3 watts, so that's usually higher than the reverse leakage, but not always. We'll see that a little bit later. So there is a negative feedback, and that means the stability, and you can actually, it takes actually an effort to destroy a Schottky. If you just push the thing in forward direction, you go to 200, 220 degrees, 230 degrees C. You really have to melt the diode and the solder inside before you destroy it. So it's very difficult to destroy Schottky. I don't recommend doing this in your design because that's not particularly a good way to get good reliability. But that is, of course, it's a very stable device. There's always this reliability versus efficiency trade-off. A lot of people, of course, want to push the Schottky diode to the limit, to the highest temperature to get the lowest VF, but that doesn't help your reliability long term. So that's something that we all have to take into account. This is a slide which I took from the IC norms on photovoltaic junction boxes on thermal runaway, and it just explains the phenomena. The same happens when you're using Schottky as an OR-ring diode, or actually other applications. And if you're using it in a power supply, it just happens every 5 microseconds or 20 microseconds, depending if you're switching at 200 or 50 kilohertz or something like that. So on the left-hand side, we see the power injected or the power dissipated, if you want to call it that side, things like that. So that's the y-axis. On the x-axis, you see the junction temperature is measured. We take first case number F2. So what happens here is you see that the Schottky diode is carrying a certain current and dissipating power. And then it actually gets switched to reverse to blocking. So you switch from forward current to reverse blocking, and what you see on the case of F2 in 0.1, it goes down to 0.2, because at that junction temperature, which is determined by the thermal resistance, the leakage current is a certain value multiplied by the breakdown voltage over it, and the junction temperature goes down and the system is stable. So what happens is you go from a point number 1 to point number 2. In this case, the junction temperature goes down. That means the leakage current will go down and will continue to go down to either a stable value or to room temperature, or in the case of a switching power supply, it will just go up again when you are working in the forward direction. Now we are going to F1, the top one, on the top left one, where you have a lot of current in forward direction in the diode, and when it hits the thermal resistance curve or the thermal resistance, then you get the TJ, in this case on 0.1 here, and you switch to reverse, the junction temperature goes up because the reverse power dissipation is higher. That, of course, is the problem area, because in this case, if the junction temperature goes up, the leakage current will continue to go up, and as a result, there will be thermal runaway. The formula that the forward losses have to be higher than the reverse losses is an approximation, but a good approximation. It's not 100% scientific, but it gives you a good idea of what happens to avoid a thermal runaway. So this is what happens if, let's say, if you're switching the device. We're going to repeat this slide, and now you have to imagine that F1 and F2 are not there. You're just doing something statically. You're just putting a diode in an oven, and then, or something what's called an HTRB test, high temperature reverse bias test. And then you see that once the solid curve hits the thermal resistance curve, the 1 over RTA curve, then you're gonna go below that, there is stability. Above that, there is thermal runaway, and this is one of the key reasons in reliability testing how you can actually determine the maximum TJ in your data sheet, which is dependent on the thermal resistance, which surprises a lot of people, of designers in this case, but it is. So, and this is what we call the static thermal runaway, where there is no forward dissipation, where you just dissipate power in the reverse direction. So, and that's where in the footnote of a lot of data sheets, you see this formula, the change P, the change in power dissipation, total power dissipation divided by the change in junction temperature has to be less than 1 divided over the thermal resistance. So that's a footnote, and this is actually determines your static thermal runaway point of your device. And you can make every Schottky go to thermal runaway. There is not, it's inherent to a Schottky, but some Schottky's diodes are easier to get into thermal runaway than others. Some it's virtually impossible to do so. So what helps in case of the thermal runaway? It's very simple. You want to keep the leakage current as low as possible. So in that case, you want to have trench Schottky because the die size is smaller, and you want to have 175 degrees C barrier material because the leakage current is smaller. The ones below planar Schottky with a bigger die and the 150 degrees C barrier material, actually they will, it's not that they are bad diodes or anything like that. They just have higher leakage currents and will be more prone to go actually in thermal runaway. But under the right conditions, also planar Schottky diodes or 150 degrees C Schottky diodes will rated junction barrier materials will not go into thermal runaway. It just, if you are really pushing the technology to the limit, then that's what you want. Trench Schottky and 175 degrees C rated diodes. Let's talk a little bit more about reliability here. What is actually reliability on a Schottky diode? So the purpose of the HTRB test, that is high temperature reverse bias test, is to detect manufacturing defects, contamination, mechanical damage, an improperly applied barrier, and that type of stuff. Those are the things that you do and test and detect via a reliability testing. All these failures result in thermal runaway, just the same as a normal thermal runaway that is inherent to the diode. So this makes the things a little bit more complex sometimes about reliability. So what we like to say here is actually, if you look at rectifiers and TVS and maybe also even MOSFETs and other discrete technology, you can assume that 175 degrees C rated product is better than 150 degrees C rated product, probably because its passivation is better. And that is good and that is fair an assumption and things like that. In the case actually of a Schottky diode, that doesn't necessarily apply. They're just two different products. They're just completely two different products in these two barrier materials. So, a Schottky diode also has conflicting problems. If you have a high HDRB test and Arrhenius, you want to have actually, the higher barrier material with the lower leakage current. That's when you get your reliability and fit calculations using Arrhenius will be better. However, if you use those, then your delta TJ, the difference between your junction temperature with on and off cycling, will be higher. And this means that actually Coffin-Manson equations will be worse. So for that actually pushes you more up to 150 degrees C rated product to reduce the VF. So there's conflicting pressures on Schottky diodes. The formula there that I show you is that I talked about earlier on about the junction temperature being dependent on the thermal resistance. Actually, the picture you're seeing there on the slide are actually test boards for high temperature reverse bias. So you see, these are ours, but I think we all do this in the business. Everybody likes to make a test board with extremely good thermal resistance and unrealistically good thermal resistance to avoid thermal runaway and push up the junction temperature during HDRB testing. So that's something you need to be aware of. It may not actually have any resemblance to actually your actual circuit or board layout, the way we test these devices at high temperatures. We'll move on a little bit more, and now we're going to go to second sourcing. Second sourcing will split in two parts. So we'll first look at forward losses, and then we'll go actually to reverse losses. On the left-hand side, you see typically these derating curves. On the x-axis, you still have ambient temperature here. Why is it, these derating curves can be completely, they are not meaningful. And let me explain this to you. This is a 1 amp diode, and you see this derating curve here. Actually, there is nothing scientific in this curve. The slope is the thermal resistance of the measurement setup, which is chosen by marketing. And the derating point is also random, and it's also chosen by marketing. So actually saying that if you're second sourcing a Schottky diode or any rectifier saying, I have a 2 amp and the other one is also 2 amp, that is not always the best way to go forward. It might get you some misleading results. So actually, what happens in modern day surface mount parts, you replace the x-axis, the ambient temperature, by the case temperature. However, the total of the thermal resistance usually depends on two parts, the resistance of the package itself and the resistance of the PCB. and the PCB thermal resistance usually is much higher than the package thermal resistance. So if you're just looking at case temperature, to be honest with you, you're also having misleading values. Also, what you have to watch out for is that the solder pads that we use and everybody else uses to measure thermal resistance is they are unrealistically big. You know, we usually measure them, for example, on a small SMA package as a 5 millimeter by 5 millimeter, whereas the recommended solder pads are just over 1 millimeter, and that's what most people use because that's how people solder them. So watch out for these junction to ambient thermal resistance values and measure them actually in your circuit. So what you need to do is, of course, to compare the typical VF curves. If people cannot cheat or lie about the die sizes in those, so that's the best way to compare apples to apples on the case if you want a second source Schottky. And then, of course, you definitely, if you're looking at a trench Schottky, then you definitely want to also look at the temperature coefficient of VF because they're not all equal. These technology have different temperature coefficients, so that's another thing you need to actually compare to get an accurate results. Also, to think about it, an SMB, I just took an SMB package. We're moving to the right of the slide now. 2 amp as an example, just as a popular part, the SS2 is 30 years old or something like that. Well, there could be 4 versions by now because somebody could make it in trench or in planar with different barrier materials and that type of stuff. So there are many different technologies that will actually complicate your choice. And as a result, there is also a Schottky part name proliferation in the business. We'll talk a little bit later about that, and that makes the second sourcing actually significantly more complex. Let's look at the reverse leakage current losses. And here you actually can easily tell that you need to compare the blocking voltage, which is your circuit design, and the leakage current. So you're going to have to look at leakage currents. And especially if thermal runaway is important in your design, this needs to be very detailed. The high IR temperature curves in the data sheets, there is thousands and thousands of them. They're difficult to make. You need a guy sit there, measuring a few samples in an oven in the hall, stabilizing it and that type of stuff. So there's tens of thousands of data sheets out there. Maybe not all of them are accurate in the business. So you want to also measure it actually in your circuit to make sure that it's done well. So the other thing is how well do you know your junction temperature? That's another thing. In the old days, when you put a TO220 on a heatsink, well, you measure the temperature on your heatsink and you are all set. Surface mount technology is a little bit more complex. Some people measure case temperature. The question is, what is case? It's very difficult to define. So the best way to do it is actually measure the leak temperature where it touches the PCB, and then roughly that's how we measure the thermal resistance of the package, and that should actually give you a good idea of what the junction temperature is if you recalculate it that way. There are commercial choices on trench barrier diodes. I just wanted to point this out to you. I say that leakage current is better on trench, and that is correct because the die size is smaller, but if I am a designer under pressure from a marketing department to make a cost-efficient device, well then you can reduce the die size of your transparent Schottky. Then you see, I have the same VS spec and a better leakage current. So then you reduce the barrier material, and then of course you get the same leakage current as your planar Schottky device, but even a smaller die size. So watch out, trench barrier is better on leakage current, but usually, but there are of course commercial compromises that have to be made. The last thing you should know is that on a planar Schottky, the capacitance is really linked to die size. It's 2 plates in parallel, so it's very simple, very straightforward with the voltage. On the bottom of the slide here, the bottom right-hand side, you see the typical capacitance of a planar Schottky device. Because the field is non-linear in the trench Schottky, the capacitance is actually less predictable and it is higher. The trench Schottky diodes have a higher capacitance. This can be an advantage or disadvantage to EMI. depending on who you speak to. The last thing is TRR. A Schottky diode doesn't have minority carriers, so it shouldn't have TRR, but they are injected via the guard band. And as a result, trench Schottky may have different guard band technology and slightly better TRR values. That's something, you know, if you have high pulsed currents and that type of stuff, that's something you should also take into account and maybe study if you're second sourcing Schottky diodes. If we now go on to the next slide, this is something also very quickly about Schottky diodes. This is an older Schottky diode, the SS14 is probably 30 years old, one of the earliest surface mount Schottky diodes after the MELFs. What you see here is Schottky diode have so-called prime bins. So there are no, in this case, 8 part names, there are actually only 4. There is the 40 diode, and the 20 and 30 volt are the same as the 40 diodes. They just have different tests. 50 is the same as 60, and 90 is the same as 100 in this slide. This is what we call the prime bin, or 40 then the prime bin, and then the 20 and 30 are the non-prime bins. In the old days, sometimes these specifications were all written just to have good yields, and then you could sell also the reject of the SS14 as a lower voltage if they didn't pass the 40 volts. That, of course, is not great for reliability testing from a reliability perspective. However, if you do something called part testing, and not everybody does this, but it's called part average testing, then you automatically test all voltages or all products to the average, the distribution, the bell curve distribution or the Gauss curve distribution, and the parts have to be into the normal distribution before you can sell them to the customer. That's another area, other thing you should be aware of in Schottky data sheets. Next slide, of course, is how do we go about? You know, this is DigiKey. You can also go to Farnell and that type of stuff. I just put in diodes, rectifiers, and then chose Schottky, and then you see there are 12,000 products also from quite a few suppliers, including ourselves and that type of stuff. So, you know, there is certainly enough choice for designers of Schottky diodes. You know, so how do you go about selecting one? This is not so easy anymore. There are too many part names, and so there is no magic solution in this case. But I go ahead and always select the breakdown voltage. You know, let's say 60 volt. You need a 60 volt diode or a 40 volt diode or something like that. And then we on our website can export this to an Excel spreadsheet. Then that Excel spreadsheet allows you to create filters, and then I go around and play around which packages are available, which currents are available, and that type of stuff. So I wouldn't select to currents necessarily, but I would first go to breakdown voltage and then maybe to packages, and then see which packages I have, and then check out what the VFs are in those packages in the leakages. Currents are in those packages. So that's how I usually go ahead to find a part. Next slide, packages. So SMA and SMB, SMC available for 30 years. SMC especially is from thermal runaway perspective is probably the worst package on the market. So what happens is with these older packages, every millimeter that the heat or of the die, which is the die is in blue in all these pictures, has to travel to the PCB, is an added Kelvin per watt thermal resistance. So you know, so long leads are not desirable. They push up the junction temperature for no reason, things like that. So that's on the left, the SMC device. On the right, the flat leads are, of course, giving some improvement. In this case, the path is shorter and quicker out to the PCB. Of course, if the leads are narrower, then you also lose a little bit here on thermal resistance junction to tie point. The exposed path, the one in the middle, the TO277, is the better way to go, but it almost also depends on the PCB. If you don't have thermal bias, these products actually don't bring you a lot. So there's a minimal improvement actually without thermal bias. You have to have an expensive PCB before you get really the advantages of your other packages. In the old days, a switch mode power supply, a heatsink TO220 is the best way to actually assemble a Schottky. If you have a lot of power dissipation, 2 or 3 watts or something, that is still the best way to get the heat out of the product. There's also a ratio of die to package cost. Trench tends to be used because you get a good shrink in the die size when the die cost is high to the package cost. So let's say if you go 40 amp diode or something like that, then you have big die, and then in a T220, and then the die cost is also big related to the package cost. In some of the smaller products, the package cost is actually the dominating factor. So thermal runaway can be chances of thermal runaway can be reduced by good design, especially by knowing your junction temperature is the most important thing, I think, in this case to say. So how do you choose a Schottky diode? It depends what your goals are. It's too simplistic here to do a color matching. It is true that if you want efficiency, you want to have 150 degrees C barrier material. That's good. Cost and service may be our best because we're just living in a world where a lot of Schottky diodes are used in cost effective or cost demanding applications. Planar technology is the way to go there. Delta TJ and TJ and reliability, maybe trench is to go there, but then of course that needs to be combined with the barrier material and the design. And is thermal runaway irrelevant? Then of course you want to have this 175 degree C barrier material. But then efficiency is also helped, for example, by trench and so on. So there are no simple link. There are usually two factors at least influencing each demand on efficiency or cost and service. But we made the most important links here, but you also have to think a little bit more about the secondary links that are still working here. When you are doing these designs, the choice of your package is critical, and also the choice of your PCB is critical. It's as important as the choice of the Schottky diode. So if you can get your thermal resistance down, then that would be the most important or the best way to actually also influence and optimize your Schottky design. I'm going to finish the presentation by giving an example of a new planar diode which we made in thin SMA package that's similar to the SMA package, just a little bit smaller and with the 1 millimeter height mounting. It's more optimized for reflow, whereas the SMA will always be there for wave soldering also. And a lot of Schottky diodes are wave soldered. That should be also be mentioned. So that's the SMA will remain a very important package here. Here we're going to look at maybe at 40 volts, the planar diodes are still very good. At 200 volts, they are maybe less competitive, but they can still be used here. And when I say this here, you have to look at these days also at Schottky diodes. You cannot get 5 amp out of this package. It's impossible unless you use like a metal substrate. But on normal substrates, you cannot get 5 amp out of this package unless you have solder pads that are 20 times the size of the part or something like that. So what you actually use these parts for is if you go to the right hand side, the typical forward characteristics, and you look at the 1 amp and the 2 amp current lines at 125 degrees C, for example, you see they're pretty good. They're just over 300 millivolts, and they're just close to 400 millivolts for 1 or 2 amps. So those are actually planar parts that are actually going to give you a very good efficiency. So derating, the option to derate against the current rating of the package is actually quite important. Of course, a lot of people have pulsed Schottky. I've pulsed, like a 5 amp pulse with a 20% duty cycle or something like that. Then, of course, you need to look at the pulsed values here if you can't avoid using that type of design. So we're finishing up with the last 2 slides here. So if you want to have 0 defects, then you first of all you need to minimize your junction temperature. Keep it as low as possible. And actually, do you know it? Is the first question you have to design to designers, because in surface mount designs, the junction temperature is not always very well known. Limit your PCB temperature to 90 or 95 degrees C if you can, of course, your tie point temperature. The thermal resistant junction to ambient is as important as the choice of technology or a Schottky device, so it is really important. Is thermal runaway a possibility in your design? If it isn't, you can make a much better design by focusing on efficiency. In this case, derate 20% on breakdown voltage. I know there are application notes saying that you can use the Schottky avalanche. Well, think about it again. You're still better derating here on a Schottky diode. And then, of course, check out your delta TJ or your efficiency, because a lot of the failures or some of the failures may be linked to temperature cycle or power cycling in Schottky diodes, which is a bigger stress than maybe than the HTRP testing in a lot of applications. Schottky diodes, do not like humidity. So if you're working in a humid environment, potting might be advisable for you. And the small ones are also easily sensitive. So these are some of the recommendations we have for zero defects. However, unfortunately, what we have to say is that your top priority of your company is cost. Then actually, it's nearly all the recommendations have to be reversed. So there is definitely a trade-off in Schottky technology, or there are some trade-offs. Not everything has to be reversed, but something has to be reversed. So this ends the webinar. We can now look at questions. You can put in your questions in your chat box and that type of stuff. The article about thermal runaway first appeared in How to Power. I'm just saying this here. That's a good American power blog about power management. If you're not subscribed to this, that's something you could potentially do here. I'm just sending you what the link here or the website is. It also appeared in the Electronic Praxis and a few other publications here in Europe. And then this actually goes to the last slide. And I think now we are approaching the time of the webinar anyway. We are now ready for questions. I'm going to check out. Okay, if there are any questions. So I don't see any questions at the moment. You can also unmute yourself and actually ask the